Welcome everyone for coming out tonight to the first public lecture in astrophysics of the year here at Swinburne. We will be talking about the dark universe, as you probably saw in the advertisement. I want to say that ever since the dawn of man, humankind, that when you look into the sky and when we studied astronomy, we always looked at the light. And it was the light that we analyzed. And that is the basis of astronomy, but only in the last few decades have we made advances in physics and astronomy to understand the rest of the universe, which does not emit or interact with light, such as gravitational waves, which you've probably heard of maybe a talk on this recently. And tonight we're going to hear about the dark universe. You may think for a moment you're seeing double. You're not. We have two PhD students here at the Center for Astrophysics and Supercomputing, Grace Lawrence and Sara Webb. And do you want to say a bit about you, Grace?
Can you hear me now?
Yeah.
Excellent. Okay. My name's Grace Lawrence. I've just started the second year of my PhD here at Swinburne in our Center for Astrophysics and Supercomputing. I'm a theorist and a simulator, so I use simulations of galaxies very much like our Milky Way to look at dark matter and where it is in the galaxy, and then try and figure out how we can actually detect it on Earth.
And Sara, would you like to say a bit about yourself?
Sure. Can everyone hear me okay?
Yeah.
Great. So my name is Sara. I'm a third-year PhD student here at Swinburne University, and I actually work with Jeff chasing the fastest burst in the universe. So some of you might have heard of fast radio bursts before, have you? They're very great. You should hear of them if you haven't. Come chat to me afterward. They're mysterious, and no one really knows what they are. So the goal of my PhD is to try and narrow down what they might not be with other optical bursts. But tonight I'm going to be your tour guide for dark energy.
Okay, so both of these two wonderful students will give you a talk on the dark universe. The talk will go for a while, and then we'll have questions afterwards.
Do you want that?
So enjoy.
Alrighty, so before we get going today, we would like to respectfully acknowledge the Wurundjeri people of the Kulin Nation. We pay our respects to elders past, present, and emerging. And yeah, thank you all for coming, and let's have fun.
So today, both Grace and I are students and part of the student committee, and obviously Australia's been ravished by bushfires as of recent. So a thing that we're doing is, if you guys feel like you would like to donate at the end of the lecture, we're raising money for a charity called Warriors for Wildlife, which is a local Victorian charity, and they look after all sorts of animals, especially the native animals. So, you know, over 1 billion animals have unfortunately perished, and there's many, many others that need, you know, help, supplies, and regeneration of their native environments. And this charity does a wonderful job at doing that, and takes a very low administration fee, which is really, you know, respectable of them. So if you would like to help a fuzzy little koala, we'll have these donation buckets at the end, and would be very thankful. Okay.
So if you leave the lecture tonight and you go home and you look up at the stars, maybe using a telescope, you might see something like this. A dazzling array of galaxies, seemingly projected onto the heavens, twinkling down at you. There might be spiral galaxies 500 light years across, like our Milky Way. There might be fluffy red elliptical galaxies full of old stars. The universe seems fit to burst with these magical sort of accumulations of light.
And then if you were to look at each individual galaxy and really look at them, you'd notice that you'd never see two alike, ever. They're so different. They're like snowflakes. Every one of them is a little bit individual, and every one of them is home to billions of stars. And these stars are just incredible.
So if we zoom in a little bit closer into the galaxies, we see these incredible, diverse populations of stars. Stars as cold as 2000 Kelvin, which is very hot, but relatively cold, all the way up to 40,000 Kelvin, which is 6.5 times hotter than our own sun, which I already thought was really hot. Stars can be as small as maybe a few times as big as Jupiter, or as large as 100 times the mass of our own sun, and they provide most of the starlight coming from galaxies. So when you look out and you see starlight, what you're really doing is looking back in time. They're like a cosmic time machine.
So we've told you about all of these wonderful things you might see when you look into the universe, but you're not here to see things. You've come because you want to explore the dark universe. But what does that mean? Is the dark universe just the spaces in between these bright points of light, in between the galaxies, in between the stars and the planets? Or is it something more? And we're very excited to take you on a tour of the dark universe and what it actually means and how it might affect you in the future. Very, very far future, but still.
So we've already established the universe is chock-a-block full of galaxies, stars, light. So what if I told you that everything that you see in the galaxy, all the stars, all the galaxies, every atom, everything you see, smell, touch, hear, the atoms that make up your human bodies, all of it is less than 5% of the energy density of the universe, less than 5%.
But you know what that means? Is that you are one of the lucky sparkly bits, which is very rare. So congratulations and welcome to the club. So Grace, what is the next biggest chunk that makes up our universe? If we're only 5%, what comes next?
So we have a very special kind of matter, and it makes up about a quarter of the universe. It's called dark matter. And that's about all we really know about it. We know that it exists, we know that it's there, but we don't know its nature. We don't understand its characteristic properties. So how do we know that it actually exists? When we look up into space and we look at a spiral galaxy, this is what we think we should see. So in the middle, it's spinning very quickly, and in the outer regions, we think it will be spinning very slowly. So all of the mass in a galaxy sort of comes towards the center, and it's a concentration of gravity there. So that pulls all of the matter more quickly around. But in the outer regions, it should be moving more slowly, because if they were moving very fast here, they'd fly out of the galaxy because the gravity gets weaker as it moves towards the edges. So that's what we thought we would see when we looked up into the sky. But instead, what we actually saw was this. The inner part was moving fast, just like we expected it to, but so was the outer part, and this was confusing. Why wasn't it moving so slowly? And so famously, in the 1980s, a Carnegie astronomer called Vera Rubin, who we now affectionately refer to as the mother of dark matter, looked at rotational velocity curves of galaxies and found this. So we sort of plot this on what we call a rotational velocity curve, and it's very easy to understand. So we have a plot here that's distance from the center of the galaxy and then velocity. So the 0 point is in the middle of the galaxy. So this is the center, and then it comes out, and this is the outer region of the galaxy. And then the y-axis is speed, so it's just how fast is this matter whipping around the galaxy. So this dotted curve is what we thought we were going to see, very fast in the inner regions, and then slowly getting slower. But what we actually saw was this. It got faster, and then it flattened out at some large radii. And what this tells us is that there's more mass in this galaxy than we can see. There's some mysterious missing mass component driving the outer regions of these galaxies to move more quickly. And this missing mass is what we've called dark matter. And the exciting takeaway from this is that all galaxies are actually embedded within an extended dark matter halo that reaches 5, 10, or sometimes more times larger than all of the baryonic content in our galaxy. So our very own Milky Way right now is sitting within an enormous cloud of mysterious ghost-like dark matter. So we've accounted for 30% of the universe now, 5% baryons, 25% dark matter, but we haven't yet addressed the elephant in the room. What's the majority of our universe?
So by elephant, you might mean dark energy, and it is an enormous elephant compared to the rest of the plot there. So it makes up about 70% of all of the energy densities in the universe, which is pretty insane. And we had no idea that something like this could even exist until about 100 years ago. So I need you guys to imagine that you're looking up at the night sky hundreds of years ago. You don't have telescopes, you're just looking up. it looks pretty steady, right? If you were to go out night after night, you might see some planets moving across, and they're very periodic, so you could map them. You might see some comets or asteroids falling into Earth, but nothing else seems to be changing. The galaxy's pretty still. Constellations aren't moving around the place, and it would be absolutely reasonable to assume that we live in this static and steady universe. However, when you start looking out with the telescopes, you start to see some little fuzzy bits. And back about 100 years ago, a very smart man named Edwin Hubble had a look at some of these fuzzier bits. And until he decided to measure their spectra, everyone thought that they were inside the galaxy, that they were just nebula. They were chunks of gas inside our galaxy. But what Hubble did was he was able to split the light coming from these galaxies and figure out how far away they were and how fast they were moving. And so this is a term you may not have heard of before, but it's called redshift. And so if you were to take a candle on Earth and you were to split the light through a prism, you would see these black lines at certain wavelengths. And so if you do that to a galaxy very, very far away, you also see the black line. And what this is the atoms are absorbing a little bit of the energy. When they have a free electron, they absorb the energy. They get very excited. Not very excited, it's the opposite, but they're excited to have the energy. They grab it. And you can't see it anymore. That energy band, that discrete band of energy is taken, so it comes up as black. So if we measure that to a galaxy far, far away compared to what we measure on Earth, we see that those lines have been shifted towards the red. And now in physics, when we say redshifted, it means that something's lost energy. When we look in our spectrum, purple is very energetic and short wavelengths. And red is relatively non-energetic and much longer wavelengths. And this happens when light moves through space. It will lose energy and stretch itself out. So Hubble saw that there were heaps of these galaxies and they all were seemingly moving away. There was only a few that were moving towards us, and they seemed to be the bigger ones on the sky. So what did this mean? He was able to determine that the universe was in fact not steady, but expanding. And the reason it was expanding was because of this thing called the cosmological constant, which you may have heard of before, which we'll discuss a little bit later. But that was revolutionary. In 1929, we went from understanding that we didn't actually know we were in a galaxy, we just thought we were in the universe, to now, oh geez, we're in a galaxy and there's all of these other galaxies out there and they're moving away from us. And what does that actually mean?
So we've now defined our dark universe. 95% of what we see is dark matter, or it's dark energy. But just to be clear, the term dark here can sometimes become a bit of a misnomer. Dark here doesn't mean it's black or grey in colour or that it doesn't emit light. The term dark is just a label that we give these things because we don't really understand them yet. They're still invisible to us. They've just escaped our reach. We haven't quite figured them out. And so, ladies and gentlemen, welcome to the dark universe, and let's dive in.
So we're going to go back before the universe existed. So imagine there's nothing. I know that's absolutely insane to try fathom. No space, no time, no stars, no planets, no dogs, nothing. It's empty. And then all of a sudden, just randomly, spontaneously, space and time started to exist. And we're going to sit through the first couple seconds of the universe together and just take note of what's happening on the screen. Okay, so this happened in less than a fraction of a fraction of a fraction of a fraction of a microsecond. Less than that. The universe spontaneously came into existence. It was very, very small. And then all of a sudden, inflation happened. And we're not quite sure why inflation happened. And there's a whole different range of theories. But all of a sudden, inflation happened. And it burst. And it went from very, very, very small to still quite small, the size of an orange, but from the very small, it grew 10 septillion times the size that it was when it was first created. So 10 septillion is a 10 with 26 zeros after it. It's absolutely insane. And it cooled down a lot, even though it's 1 trillion degrees, a little bit hot for me, but it went from 100 trillion degrees down to 1 trillion degrees. And now what that means in physics is that with a cooler energy state, we were able to start making this thing called quark soup. And Grace is going to further explain why this is important and why it actually means you exist today.
So after inflation happened and we cooled down, we had this still hot but cool quark soup. But this matter had to burst into existence somehow. It had to come from somewhere. And the way that it popped into existence is through a process called particle annihilation. And this is where pairs of particles just pop spontaneously into existence in the universe. They come together, they annihilate, or they cancel each other out, and then they disappear. And they leave nothing but pure energy behind. So a really easy way of sort of visualizing this is by taking a positive and a negative. So we're going to take this positive, purple, and we'll call it matter. And then we're going to take this green negative, and we'll call it antimatter. Now, they've popped into existence, they've come together, they've annihilated, and then they've disappeared. All they've left behind is pure energy. And now this happens trillions and trillions of times. There's particles popping up and annihilating all over the place. But a really interesting sort of feature of our universe is every now and then, 1 in every billion pairs of particles that pops into existence doesn't have its antimatter particle to annihilate with. And so it's searching around for its friend it wants to annihilate, but it can't find anybody. And so as these particles pop into existence in the universe, they start to annihilate, but some of them are left over. And so what happens when this happens trillions and trillions of times is you slowly build, you create the matter in the universe, the first subatomic particles, quarks, which then go on to build protons and neutrons, which form atoms. But this doesn't just happen with baryonic matter. It also happens with dark matter. So the universe hasn't even existed for a second yet, but it's popped into existence, inflated, cooled, and it's created subatomic particles and dark matter. So let's take this snapshot. This is a snapshot of our entire universe. We start over here on the left with the Big Bang. It rapidly expands in this grey region. Matter and dark matter form, and then time sort of evolves the universe. Excuse me, time evolves the universe, and we sit somewhere here today. So we know now that the universe is made of baryonic matter, dark matter, and dark energy. We see it. But surely it can't be that simple. Scientists have spent thousands of years trying to understand the universe. It can't be as easy as adding 1, 2, 3, and there you go. Otherwise, Sarah and I wouldn't have jobs. So, Sarah, what makes a universe a universe?
You're not going to like it, but I'm going to tell you it's as simple as 1 and 2. You don't even need 3. So, the first thing you need is a box. And so our box is the universe. It's the space, the time, everything that exists, that holds our existence is our box, right? And then the only other thing you need is stuff to put inside the box. That's it. You only need something to hold it and something to go inside, and that's a universe. But what makes a universe incredibly special is the laws of physics that that box has to obey. It must obey the laws of physics that are defined at the creation of the universe. And these are naturally incredibly hard to figure out. No one gave you a manual when you enter physics school with "this is why the universe works, congratulations." And trying to figure it out took very smart people. And so I'm sure you're all aware of Mr. Einstein and his wonderful work in special and general relativity. So today we're going to talk a little bit about general relativity. His work in this describes how that box is able to bend and contort depending on what you put inside it. So in essence, it's still a box. It's still something holding everything inside it. But instead of just holding it and not really doing much, this is telling it how to move. So Einstein's theory is able to predict how matter is going to move through space and time, because that matter is going to bend space and time. But by bending space and time is now telling that matter how to move. it's this symbiotic relationship that must exist for things to be able to exist in the universe. And so there's one equation that really defines it, and it's called Einstein's tensor. And so you could apply this equation to every single point in the universe, every single atom in the universe, and figure out where is it bending, where is its gravitational potential bending, and where is it going to go. And so what's exciting is all of us are made out of trillions of particles. I know we've said trillions a lot today, but we've got trillions of things in the universe. So your trillions and trillions of particles make up the human body. Each one of your particles is not only gravitationally attracted to each other, but it's attracted to something on the other side of the universe, or it's attracted to Jupiter, Pluto, it's attracted to, I don't know, your favorite celebrity in Hollywood. You know, we're all interconnected by this thing called gravity or general relativity, which is quite remarkable. And so now we have a box and we can put stuff inside of it and we can predict how that stuff inside is going to move. But there's one other thing we need to know. So Einstein's solutions are not exact solutions. He doesn't just give us an equation and say, here's your universe. You need to predict some things to then get an exact solution. So we need to know a little bit about the universe we live in. So the first thing that we assume is that we're in a flat universe. So what that means is that you can't just poke a hole through space and time and end up somewhere else. I'll most likely never be able to create a wormhole and end up at the Big Bang or fold back in on itself, which some sci-fi movies like to play with. And it's a great idea, but for physics, we assume that we're flat. We're homogeneous, which means that we're pretty similar everywhere. Everywhere you look, we obey the same laws of physics. You look out into the night sky and it looks almost identical everywhere. And the other thing that we must obey is that we're expanding. So Einstein included this thing called lambda, the cosmological constant, which I spoke about earlier. Now, the first reason why he included lambda was to make this equation steady. So Einstein came up with these equations before we even realized that there were other galaxies and they were expanding. This was in 1915, well before Hubble came up with the expanding universe theory in 1929. So Einstein was just being told what observational astronomers were seeing, you know, a seemingly steady universe. And when you solve these equations without the constant, you don't get a steady universe. You either get one that is expanding and accelerating, one that is expanding and contracting, or one that just starts to contract. And so the cosmological constant was put in there to create a steady solution, which ended up being a fantastic forethought by Einstein, even though he called it a blunder, because now we're able to test our theories using this cosmological constant. And so we go back to the universe, and this universe here is just a slither. You can imagine if you took a pinpoint in the sky and you were able to look all the way back to the beginning of the universe, this is the cone that you might see. And what's interesting is even though we would love to see the Big Bang, we would love to look back in the cone and see the Big Bang, wouldn't that make physicists' jobs easy? We wouldn't need particle accelerators or experimental astrophysics or anything crazy complicated. We'd just look and see what happened and we could explain why we're here. But unfortunately, there's something called the cosmic microwave background radiation, which blocks us from seeing any further. And the reason it blocks us from seeing any further is because that was the first light ever created in the universe, ever released into the universe. And so this thing here, this turquoise little disk that you can see, is actually an incredibly important part of our universe because we're able to test our physics on it. So now imagine this is like a special projection. This is, if you were to wrap it all around the sky, this is what it would look like, and we've just flattened it out for you. So what you can see here is a lot of dots, a lot of blue and red dots, and you probably think you can probably see some structure in that. You know, that blue void looks a little voidy if you were to describe it, but what we're actually measuring is the microwave background radiation. So what that means is at the beginning of the universe, photons for the first 400,000 years were coupled to their atoms. They could not be released. And all of a sudden, one day, click, the universe went transparent. And those photons were able to escape. And they were incredibly energetic. They would have been like gamma rays, incredibly small wavelengths and very energetic. Now, that happened 14 billion years ago, which is a very long time. So these poor wavelengths have been traveling through space and time for 14 billion years. They're exhausted. They've started to lose their energy and stretch out into the microwave. So microwaves can be between 1 and 30 centimeters long, which is pretty long. It's measurable on a human scale. And so we can use this information now to figure out what is the temperature of the universe today and what is the temperature of the universe when it went transparent. So the temperature of the universe today is about 3 degrees Kelvin. Does anyone think that's cold or hot? No? Cold. It's pretty cold. It's actually negative 270 degrees cold. So it's absolutely freezing. And that's the universe today. However, if we convert those microwaves all the way back into their shorter wavelength originals, we would find out that the universe was 3,000 degrees Kelvin. So that is the surface temperature of some of the stars that are out in the universe. That is scalding hot. And what we can do is actually measure what was the temperature over this map. And even though I said before, some parts look like they have structure and, you know, this is a little voidy, if you were actually to measure the differences, it is a fraction of a degree. So it is almost immeasurable with an everyday thermometer. If you were trying to measure the difference, you couldn't. It would be the exact same temperature. And what that means is that that's a homogeneous and an isotropic universe, which is exactly what we're looking for. That's exactly what we think our theories predict that the universe will be. And this is proving to us that at one point, the universe was completely uniform. And every way you looked, it had the same stuff in it. But it wasn't completely perfect, because if it was completely perfect, again, we wouldn't be here, and that would be a shame. So how do we go from this baby photo, 400,000 years old, to now we look at the universe and it is a middle-aged universe, it's chilling, it's got lots of spots everywhere, lots of voids. How do we actually go from that, Grace?
So when we look up at the cosmic microwave background, Sarah's just told us that if we took a thermometer to the reddest red and the bluest blue, it probably wouldn't register much difference. The temperature was pretty uniform. But on top of the tiny temperature fluctuations in the cosmic microwave background, there very importantly was tiny density fluctuations. So all of the particles weren't uniformly distributed. They weren't equally as far from their neighbors as each other. So 1 or 2 particles would have been just a little bit closer together than the others. And so their gravity would have attracted each other. They would have fallen in, and all of a sudden you have 2 particles together. And now they have a little bit extra gravity than the other particles. So they start to pull on all of their neighbors, and you start to form these tiny little clumps in the early universe. And so they get more and more gravity. They start to pull in more and more matter. The clumps get bigger, the universe expands, and we start to create structure. So we can make this beautiful sort of cutesy baby image of the universe, and we know what we look out and see today. But in order to sort of get from A to B, it's very, very hard and sometimes impossible to actually observe these points. So what we do instead is we use simulations, and simulations let us see the teenage years of the universe. So what we do is we create tiny little particles in a computer, and we give them physics. So we know, or we think we have a pretty good idea of the physics that sort of runs the standard model. And so we code the physics into these particles, and then we let them run. We seed a baby universe, and then we evolve it in supercomputers. So Swinburne's lucky to have our own supercomputer called OzStar, and we make baby universes in it. So if we start with this sort of homogeneously distributed blue cloud, and then we hit play, we see structure start to form instantly. The gravity and the clumping starts to take over, and you see sort of these small lighting up parts clumping together and coming together and forming these structures. And as they get ever larger, when they get too big, the gravity of them causes them to collapse down, and they form these filaments that weave their way through the universe. You can see these filaments as the blue parts have sort of all joined together. And we call this sort of the filaments as they join together the cosmic web, which is also Sarah's Twitter handle, and you should all go give her a follow. So this is what we think the cosmic web looks like. This is from the Millennium simulation. So we see the beautiful filamentary structure. sort of weaving its way across the universe, and we zoom in, we see that there are purple bits and we see that there are yellow bits. Now, the purple is dark matter and the yellow is baryonic matter. And the dark matter actually fell into these structures first, and then the gravity of the dark matter pulled the baryons, so it pulled the galaxies and the stars into the structure with it. So we can see these filaments all coming together. We see voids. Voids are seemingly empty space. We don't know what's in a void. And then we come in and we see a node, which is where filaments all join together. And each of these tiny dots of light is an entire galaxy, like our Milky Way. And this yellow point here is what we call a supercluster. So if one galaxy clumps together with hundreds of other galaxies, it makes a single cluster. And then if that galaxy cluster clumps with another galaxy cluster, clumps with another galaxy cluster, we create a supercluster. So as we zoom back out, I think it's interesting to point out our own cosmic address here, because we're sitting in a supercluster. The planet Earth is in one of those big yellow nodes. So we're in the Virgo supercluster, and we're in some smaller cluster within the Virgo supercluster, and we're in the Milky Way galaxy in that cluster. In the Milky Way galaxy, we're in the Scutum Crux spiral arm, and then we're around our sun's own solar system, and then we're on planet Earth. So thinking about it on that scale is very humbling. But it's also sort of fascinating because it tells us how unique and how special our universe is, that we've evolved in such a way that we create these structures and these filaments and the ability to have planets like Earth exist. So we know that dark matter and baryons work together to form these structures. But what about dark energy? Does dark energy influence structure formation? Does it have any effect on this cosmic web that we see?
It does, but not in the way that dark matter does. And so to explain this, I need to take you guys on a bit of a tour of what the universe has done in its lifetime. So at the beginning of the universe, there wasn't much matter. It was all energy, and we call that radiation. And so if you were to grab a little chunk of the universe at the very beginning of time and you were to measure what is the pressure on this chunk of space-time from this radiation, you would end up getting this curve. You grabbed a chunk across billions and billions of years. And so at the beginning of the universe, that chunk of radiation had an overwhelming effect on the box that we're measuring for our universe. It was the majority of this thing that we call energy density in the universe. So it was the controlling factor. And then, as we all know, matter started to come into existence, and atoms were formed, and then stars, galaxies, planets, and it got heavier and heavier and heavier. And this is where the blue line comes in. So again, if you grab a chunk of the universe at the beginning, the middle, and now today, and measure it, the matter at one point took over from the radiation. And so this point here was actually where the universe started to slow down for just a little bit. The universe was expanding, seemingly steadily, and then it started to slow down as matter took over. But again, matter is now falling, and the reason it's falling is because of this thing, dark energy. You can imagine you have a kilogram of something and you put it in a box, and then you measure how many kilograms per cubic box is there. Now you enlarge that box by 10 times, and you've got the same amount of matter spread out across it. Now if you were to take its section, you'd have much less energy density per cubic whatever you're measuring. And so this is where dark energy comes in, and you guys might be expecting an insane, crazy-looking thing on the graph. And actually, it's very overwhelming. It's very constant, just like the name suggests. It has always been, always will be, the exact same energy density, whether you grab the box at the beginning of the universe or towards the end of the universe. The same pressure pushing outwards on space and time will exist. But what changes is how much pressure is pushing in on space and time from matter and radiation. And as that gets less, dark energy gets to take over. And you might notice this cheeky bit at the end where the purple overtakes the matter. And that means that now we're in a dark energy dominated universe. So if you were to take a box, the overwhelming pressure, dark energy. So it means that our universe has kind of had three careers in its lifetime. So it started out as a radiation dominated universe, saw that through for a little bit, and then we changed to a matter-dominated universe, and we started to slow down in our acceleration. But sure enough, just a couple billion years ago, dark energy started to take over again. And now we're in an accelerating universe, so a dark energy dominated universe. And you might be thinking, what is the next career stage of this universe? And you can probably guess it doesn't have one. It just stays in this constant dark energy dominated state for the rest of its existence, because we can't spontaneously create more matter in all of the boxes that we need to. Radiation is still going down, and so dark energy is going to be the overwhelming pressure until the end of time.
Okay, so far in this lecture, we've evolved the entire universe in terms of its dark components from the Big Bang until the present day. So that's a lot of time to cover. So let's take a quick recap of the state of the universe before we go a bit further. So we know that nearly 14 billion years ago, our universe just popped into existence. We know that galaxies are formed and fall into these large-scale structures that are both dark matter and baryonic matter. We know that all of our galaxies are embedded within these enormous, extended dark matter halos. And we know that our universe is expanding at an accelerating rate because of some mysterious pressure that we're calling dark energy.
So now we're going into the interesting part of the lecture, because we exist in a very, very special time in the universe. Not only do we exist, which happens to be useful for our existence, but we exist in a time of humanity where we have unprecedented access to technology and to the ability to build different types of technology, so telescopes, detectors. And so now we get to tell you exactly how we understand the universe through this technology. So Grace, how do we detect dark matter? I'm guessing it's probably easy because there's so much of it, right?
Absolutely. So we absolutely think that we can detect dark matter, and we think that we can do this a few different ways, but I'm going to focus on something called direct detection of dark matter today. But before we can go out into the universe searching for dark matter, we have to have some idea of what it is. Otherwise, how do we know we found it when we do? And that means we have to make a few key assumptions. Think of a few models or a few candidates we think dark matter could be. So we're going to assume that dark matter is cold dark matter, so that it's a particle with fairly low energy, so it's cold, that clumps together. And that matches with our observations. So we're assuming cold dark matter, and we're going to assume a model of something called a WIMP, or a weakly interacting massive particle, our WIMP particle. So these WIMP particles we think are about 100 times the mass of a proton, which sounds like a lot, but is actually teeny tiny. And we think that it only interacts on the weak scale. So it has, we call it an interaction cross-section of a picobarn, which means the amount of space in the dark matter particle that's available to be interacted with or to run into is 10 to the power of minus 36 centimeters squared. So the chances of running into one of these are near impossible, but we're going to try and do it. So we've already established that our Milky Way is sitting within an extended dark matter halo. And we know that the sun sits in a spiral arm that rotates around. And so as the sun moves through this halo of dark matter, it's going to sort of seem like there's a headwind of dark matter particles rushing through us. And we call this the WIMP wind. And so as our sun sort of moves through the galaxy, and the Earth's just sort of along to the right at the moment, but we get these WIMPs that are flying through our solar system all of the time. So if we had the ability to put on some special goggles that let us see dark matter, when we looked out into the universe, maybe we'd see something like this. Our cute little paper airplane WIMPs whizzing around the Earth, flying all through the universe. Now, this is a cute cartoon, but let's get a little more technical with it. So this is a beautiful simulation by Castro. It's a rotating spiral galaxy, very, very similar to our Milky Way. You can see all of the bright bits, so the stars as they move around the galaxy. And I want you to focus in on the blue background, and you can see the cosmic web there, which we know contains dark matter. So we zoom in and we're searching for our sun. So here's our sun. Now again, focus on the blue background. You can see that the dark matter is whooshing through the sun all of the time as it moves around the galaxy. But what we really care about is the Earth. So we know that we have our 8 planets plus Pluto, sad face, rotating or orbiting about the sun. And so as we zoom in on the Earth, keep an eye on how fast the background is moving. So when the sun moves in parallel with the Earth, so the northern hemisphere's summer, the Earth is moving at an increased velocity with respect to the background. And so more dark matter is going to fly through the Earth. And the opposite is true for when the sun moves against, the Earth moves against the motion of the sun. We come down. And so dark matter traces out this sort of sinusoidal curve. The flux of dark matter modulates through the Earth over the course of a year. And we call this signal annual modulation. And it's a signal that a lot of people are looking for as evidence of WIMP dark matter. And one experiment has actually claimed to have found it. And this is the DAMA experiment. So it's an Italian particle physics experiment. It's hosted in the Gran Sasso laboratory in L'Aquila in central Italy. So here, I was lucky enough to work in the same laboratory 2 years ago. Very, very cool technology. And this is their result. So they have, basically this is just dark matter count, so how much dark matter they detected over time. And we can see, so this is a year from one peak to one peak, 365 days, and they found this modulating signal. And amazingly, it fits with the theory that we predict. And they found this signal using a process called direct detection using nuclear recoils. Now, before we claim Eureka, we found it for dark matter. There's a bit of tension with this result. So as you can imagine, a lot of projects around the world are searching for this signal and searching for dark matter. And a lot of other projects have gone out looking for this and not found the same signal. So there's a small amount of skepticism in the community as to whether or not this is annual modulation due to dark matter. So we haven't cried Eureka yet. But let's talk about what direct detection is. How does it work? If dark matter is so mysterious, how do we detect it? So you really only need 3 key things. You need a detector material. So what we use is sodium iodide crystals that have been doped with thallium. But all you really need is something for the dark matter to interact with, and the structure of a crystal works really well for our purposes. You need some dark matter, some ghost-like particle that's going to whiz through the Earth. And then you need a detector of some description, something to detect the signal when it comes. So what happens is dark matter flies on through the Earth, it hits the detector, some small fraction of it, remember 10 to the minus 36 centimeters squared, interacts with that crystal and releases a burst of energy which we can detect. And the rest of the dark matter just floats on through the Earth as if nothing has happened. And this is how direct detection works. Now, we know that we can detect it in these fancy high-tech laboratories, but I thought it would be fun to do a very small experiment tonight. So I did a little bit of math beforehand, before tonight, and I figured out that we can detect 0.03 dark matter particles every day with 1 kilo of a detector. So I thought we'd turn the auditorium into a detector. So if we assume that, let's say there's about 300 people here, that's the capacity of the audience. Might be a bit of an overestimate, but 300 people. For uniform's sake, I'm going to say every human weighs 70 kilos, and I'm going to be talking to you for roughly an hour tonight. If I do the math, that means that just during this lecture, 30 dark matter particles are going to come and interact with you, which is pretty cool. And you're not going to notice it, you're not going to feel it. Might knock an electron off your shoulder, might knock one off your shoe. You won't notice it, it'll happen without you even knowing. The dark matter particles are flying through you right now, and 30 of you will have, got one, Eureka. 30 of you will have that interaction tonight, which is pretty cool. So Australia is actually involved in a dark matter direct detection effort, and it's part of my PhD work. I'm working on a project called SABRE, which stands for sodium iodide with active background rejection. So sodium iodide is the thing that we make the crystals out of, and active background rejection is some technical residual rejection stuff that you can ask me about later if you're interested. So what it is it's a detector that's being half assembled in Italy and half here in the Stawell gold mine in Victoria, so just a few hours up the road. And what we do is we take those crystals, we put them in a vessel, and then we put them underground, a whole kilometre underground at the bottom of a gold mine. And why do we put a detector that we want to detect things coming from space underground? And the answer is cosmic ray muons. So there's radiation coming across the Earth from space all of the time. It's not harmful, we don't see it, it doesn't affect our day-to-day lives, but when we have very sensitive detectors, we pick that up. So we found out that there's about 30 dark matter particles that are going to interact with you all for this hour. But for every second that you've all been sitting here, 200 cosmic ray muons have passed through each and every one of you each second. And that cosmic ray muon energy is going to blind our detectors. But if we put our experiment a kilometre underground, all of the rock above blocks it out, and it lets us just see our dark matter signals when we find them. So it's a pretty cool experiment, and Australia and Victoria might be a part of the team that gets to prove whether or not the Italian experiment found dark matter or not. And that's a really exciting prospect. So we know that dark matter is this tangible thing, or we assume that it's this particle that we have the ability to detect in a myriad of ways. But dark energy, can we detect that? What projects are going on? How are we finding dark energy?
So dark energy is a little different. We won't get to say eureka like Grace hopefully will one day. Because as we said before, dark energy is this constant and it's built into the fabric of space and time itself. So you can imagine if you were to cut out a piece of space-time fabric and unpick all of its threads, a couple of those threads would be dark energy. And we can't do that, unfortunately, but we can see its effect on the universe because it does have such a large effect on the universe. But it's quite hard to measure. So one of the experiments that we want to do is measure how far away everything's moving from us. And we want to do it to a high redshift, which means we want to look back quite far in time, like 6 billion years ago. We want to see how far away those galaxies, what is their movement speed away from us. And to do that is quite difficult. We don't have a ruler that's, 6 billion light years long that we can just tape out to the galaxies. And so what we need to do is come up with a really smart way of trying to measure something we can see. And so the way we do that is through a thing called a standard candle, because if we know how much something, how bright, how luminous something is, and it's never going to change, it's always the same, and then we move it further and further away from us, we can then infer from that how far away those things are. And so we need something in the universe that acts like a standard candle for us. And the universe is a very exciting and energetic place. There's these things happening all the time called cosmic explosions. And as you could probably tell at the start, there's a lot of stars. Every galaxy has roughly 300 billion. Some have up to 1 trillion stars. So there's a lot of stars out there. And stars have to die at some point in their lives. And when they do die, it can be absolutely spectacular. So not only do they bang, but they explode so bright that the light from that star will completely outshine the entire galaxy that it's sitting in for a couple of weeks, which is pretty amazing, and it works perfectly as a standard candle if we find this special type of supernovae. That's what it's called when a star dies. It goes supernovae if it's the right weight. And so we found this special type of supernovae in the universe. It's called a type 1a supernovae, and it comes from a very specific star. And we know that it always explodes at a very specific mass and lets out a very specific amount of light. And that is absolutely perfect for what we want to do. So something we can do is actually just observe the universe. So there's a project that I worked on a few years ago called the Dark Energy Survey, and it surveys for dark energy. And what it does is it takes photos of the sky as many nights of a year as it can, and it continually goes back to the same spots. And it looks for these things called supernovae, like I said, and it looks for the special ones, the type 1a ones. And over the time, it might go back every 2 to 3 days to the same location every week or so, and it will detect that supernova, and it can pinpoint how bright it was. And it builds up a thing called a light curve. So this thing here on the right is our light curve of the supernovae getting brighter and fading again. And with the type 1a supernovae, they have a very, very specific shape to their light curve. So here we can overlay 29 different light curves, and you can see, although their brightness has changed a little bit, depending on their properties, they all have roughly the same shape. And that shape is correctable. So we can standardize that shape. That means that every light curve we get, we run it through some type of standardization, and then we can use that as our distance metric. And there was one point in my life where I never wanted to see another light curve like this again, because I had simulated 21 million of them in my computer and had forgotten to press save. So I needed to do it again. But they are very, very special. And another great thing about astrophysics is that we can simulate these things. So my job years ago was to try to figure out, if we're getting these coming in, how often are we typing them correctly? Because they have this perfect shape, but if you observe another supernovae on the same days, it might look like that other supernovae. It could trick you, it might look very similar. And you want purity in your data. And the reason you want purity in your data is for the next reason. We now want to plot these and figure out how far away they are and how bright they were at that time. Because if we can do that with these type 1a supernovae, we can then determine the cosmological parameters of the universe. So that means we can figure out how much dark energy there is, and how much matter there is, and what is our universe going to do? Is it going to collapse back in on itself? Is it expanding? Is it accelerating? And by now, I've told you the universe is expanding and accelerating. And the overwhelming amount of evidence for this is from supernovae cosmology. So in the red here, these are higher redshift supernovae. My friends who work in high redshift might argue that 0.1 is definitely not high redshift, but it absolutely is to me. And what you might see, thank you, Diana. And what you might see here is that they follow this grey line really, really closely. And that grey line is if we take Einstein's equations with the specific solutions from other physicists and put in homogeneous, isotropic, flat, expanding universe, the equation we think has to solve our universe, it follows that equation there. And we end up getting that our universe is made up of roughly 30% energy density between baryonic and dark, so that's exactly the number we need, and about 70% dark energy. And it means that we're accelerating as well. So this is pretty overwhelming evidence to say that we do understand the physics of the box that we live in, which is pretty amazing that us little humans stuck on this little planet Earth around the little star sun can figure out the entire fabric of space and time and use that to predict what's going to happen next. And so I probably don't need to tell you what's going to happen next. The galaxies are going to keep moving further and further away from each other. And would anyone like to know how the universe is going to end? Yes? Okay. It's going to get really, really cold. And the reason it's going to get really, really cold is because everything is going to move further and further away from each other. Now, this is not going to happen in our lifetime, or maybe our son's lifetime. Actually, absolutely not our son's lifetime. So I've actually done the math on this because I was very curious. And the number is so big, I can't pronounce it for you. And it's just ridiculous. It is trillions of trillions of trillions of trillions of trillions. You get the point. Years.
How many O's?
How many O's? Something.
After one.
I think it was like 70 or 80. Something just. Yeah, a lot of O's. Which is great because it's not going to happen to us, so us and our children will be safe from the expanding of the universe, but it does mean that one day, if we were to take the furthest galaxy we can see right now on Earth, and we can see some really far galaxies, we take the Hubble Space Telescope and we look for these things, pretty much at the beginning of the universe, at like 12 billion years ago, we can see things that we think are galaxies starting to form. So if we take that one galaxy, we go on a cosmic tour of the universe, we come back in maybe a billion years to the same spot we are now, and we look out, there's a good chance that the universe has expanded so much that that galaxy has fallen off our observable universe. And that's going to keep happening and happening until all of a sudden we're alone in our Milky Way and it starts to tear itself apart as well. So it's not a happy note to end the lecture on, but I'm glad that I got to share my excitement of the big freeze. So some people call it the heat death because it gets really cold and it's ironic. Some people call it the big freeze. And some people say it's going to be a big rip. But what's important to remember and to tell your friends when they try to argue with you is that the universe will not rip itself apart, that we know of. We're pretty sure it will not rip itself apart. So that means that the fabric of space and time will just keep expanding and expanding. But nowhere in our physics or our evidence do we have an inkling that the fabric of space and time can actually dissolve itself, which is also interesting.
So you came here tonight to learn about the dark universe. and we've shown you everything that we know or that we think we know about dark matter and dark energy. And it turns out the universe isn't actually so dark. It's actually full to bursting of interesting physics and things that we can observe and things that we can infer. And I think it's a really nice point to make here that how wonderful and how amazing and unique our universe is, that these fractions have allowed us to evolve our universe to this point where we can sit comfortably in our cosmic web as humans and build telescopes and look out and discover all of this. But I also think it's almost arrogant to assume that we might be the only universe. What's to say that, millions of other universes didn't pop into existence at the same time that we did? And maybe they had different fractions of dark matter, dark energy, baryons in them. If one popped into existence that was just dark energy, it would have torn itself apart in a fraction of a second and then disappeared again. Maybe there's ones out there that have different fractions of these, or an extra part that we don't even have in our universe. The possibilities are endless, and that's what makes research and astronomy and astrophysics such an exciting thing to learn, because the possibilities are endless and you don't know what's just around the corner.
So you're telling me there could be a universe purely of dogs?
It's entirely possible.
I'm happy. I'm a search for that universe. If you guys like searching for things too, just like us, it's sometimes important to remember that we actually don't know a lot, even though we think we know a lot right here today. And I've told you all of these things that we've only learnt in the last 100 years. And I don't know about you, but that absolutely blows my mind that, my great-grandmother had absolutely no idea that we were in a galaxy. Even my nana, when I told her, this is our Milky Way galaxy, she was astounded because that wasn't common knowledge in the 60s when she went to school. Like, our knowledge has grown exponentially and it's insane. But what comes with knowledge is things that we don't know yet, which is the really exciting part about science, is that we know that we don't know some stuff, but there's also a lot of stuff out there that we don't know that we don't even know yet. And that stuff can surprise us and take twists and turns, and that's why science is so wonderful, and especially astronomy. So we'd like to leave you with the thought that if you want to explore the things that you don't know and that you don't know, maybe you should visit Astronomy Swinburne online. So we have a range of all sorts of courses, and if you're a young student looking to, go into the field of astronomy one day, you can do different types of research projects. Even if you're not a young student, you can still get a master's degree in astrophysics online from your bedroom, which is kind of amazing. And so please go on there and explore, and you can email us, all that sort of thing. And if you enjoyed Grace and I and you want to follow our science shenanigans and you have the Twitters, you can follow us on the Twitters. I'm still learning how to use it. I spelt my own username wrong before. Thank you, Grace, for fixing it. But it's a great way to stay up into date with what's actually happening, because we do a lot of different public talks and a lot of different things are happening. And if you like to just learn random fun facts, definitely give us a follow. And we would love to welcome any questions you have about the talk, about our research, about aliens, black holes, maybe later, but we'd love to welcome your questions. Thank you.
Thank you.
Okay, so I'm going to open the floor for questions. But as you can tell, we were short microphones, or maybe you couldn't tell. And so I might be able to run this around. Sorry about that. Yikes. Sorry about that. So we're short microphones. And so if you have questions, I'll try to run over there and hand this to you. And you can speak up through that. And then you can ask Grace and Sarah anything you like. So I'll start right here.
Thank you very much. Excellent delivery. Enjoyed it. Well done.
Thank you.
I'm thinking back at the beginning of the universe when there was that situation where we had baryonic matter and antimatter. I would have thought that quantum mechanics would suggest that there must be a reason why there was an excess of baryonic matter after a bit of time. Do we understand the mechanism that caused the baryonic matter to actually have in excess of antimatter?
Would you like to take this one, or would you let me?
Well, we don't know.
Well, yeah, the short answer, can you guys hear us?
Yeah, it's this one.
No. Can you get lower?
Okay, so the short answer is we don't know. So quantum mechanics can describe things that are happening very, very well, and we can make this quark soup. Hello? Hello, I'm Adele. We can make this quark soup at the CERN experiment. Oh my goodness.
Hold it.
So have you guys heard of the Large Hadron Collider? Yes, it does some pretty amazing stuff. And so if you smash together enough atoms together, enough subatomic particles together at the right temperature and at the right speed, we can make this weird soup. We can make particles come into existence and annihilate themselves out. And we can see that there's this weird, you know, not anti-symmetry, but this weird thing that happens where matter does come into existence spontaneously. And we don't really understand exactly why that happens, but it's pretty incredible that it does. And it's also important for all sorts of other reasons that we study astrophysics. So have you guys probably heard of Stephen Hawking? You know, just an absolute legend. So he came up with Hawking radiation, which the best way to describe it is hairy black holes. And it just means that this process of antimatter and matter coming into existence is happening all the time. But around a black hole, if it happens too close to the event horizon, and you do have a pair, you do have your antimatter and your matter, one of them is going to slip right in, and then you end up losing energy from the black hole, and you gain energy and entropy on the outside, which is crazy. But again, we don't know why, but it's cool.
Great. Another question? I'll go over here. Yeah. Thank you.
Thank you. Is it possible that there are parts of the universe that are antimatter galaxies, but not like matter galaxies?
Ooh, that's a good question. Would you like to answer it? I can answer it if you want. Okay, that's a really good question. And the short answer is, from the physics we understand and what we actually see, no. Because we see that the universe is isotropic, which means that the laws of physics look and are obeying the same laws everywhere we look. And we can only see the edge of observable universe, so we can only see up to this limit, but up to that limit, and everything we've seen so far suggests no. But you might be a fan of a thing called multiverse theory, which, you know, there's a whole heap of them, and one of them is that universes touch each other in bubbles, and that you could accidentally cross into another universe, and then just the physics that makes you completely changes, and you could just disintegrate or turn into a dinosaur or something insane like that. So, no, but yes, in a weird, wacky sci-fi movie.
That sounds good. Fantastic. Oh, question right here.
Thank you. How do you determine when a galaxy is being redshifted, that the redshift's due to expansion and not just aging light travelling through space?
That's a good question. So the redshift happens, the redshift happens from both, but we're seeing we can actually, how do I explain this correctly? Yeah, so what we didn't...
You asked about tired light.
Yeah. So what we didn't explain when I gave you the equation of the universe was that there's a parameter called Hubble, the Hubble constant, which is actually how fast the universe is moving at any one time. And so if we do some complicated math, then we can figure out what is the percentage of the redshift that is from the natural movement and what is from it moving away further from us, and then what is it from the actual light traveling through the universe. Maybe come chat to us later. Sorry.
Okay. Yeah, breaking it into two
Yeah.
components is what she's getting at. Yep. Oh. Okay, I'll go around this way. You're closer. It's easier for me.
General question. How many types of detector are there at Stawell?
So currently there's only one going on, but there's a few planned.
I
So
don't mean just for your experiment, but isn't there a neutrino one?
So not at the moment. We've only just established, maybe in the last year or so, the actual laboratory that's being prepared there. The experiment's not online at the moment. It's still under construction. So we will be able to maybe detect, but at least search for dark matter there, as well as cosmic ray muons as well.
seeing other galaxies were only discovered to exist much less than a century ago, and no one has actually seen much of one rotating a full circle. Is the idea of understanding how fast they are rotating in the centre and out the perimeter entirely a matter of studying their shapes, or is it a matter of successive observations at 50-year intervals? Is it the flattening of the arms, or is it other kinds of evidence that tell you how fast they're rotating?
Do you want to take the H21 centimetre? Sure. So you know the plot that Grace showed you where it's got the 21 centimetre arm. So you're right, we can't go back to a galaxy and see it rotating and rotating around. But what Grace described, do you want to describe it better, the rotation curves?
You do 21 centimetre.
Okay,
Yeah.
so we can see visible light, and then we can also see different types of electromagnetic radiation, and one of them is from a hydrogen interaction, and it's 21 centimetre, so we can use the radio telescope to try detect when is that happening, and we end up seeing the gas that's diffused very, very far out from the actual light of the galaxy, and that's how we can get that plateaued curve to determine. And then we do that not on one or two galaxies, but on many, many, many galaxies, and build up like a statistical property of why and when is that happening, and at what, there's a thing in a galaxy called like half-light, so how much light is coming from the galaxy, when is it happening when we're not seeing light anymore, and then we can understand that because we can see from the red and the blue shift of the light, if we were to take spectra of the galaxies, this is another thing, you can take spectra of a galaxy and you can actually see in the red and the blue shift of it moving away and coming towards you. So we're pretty confident that they're rotating just as we expect.
Yeah, just to add to that, a spectrum taken at a snapshot in time can tell you how fast each part of it's moving, because you can measure the velocity it's moving away from you or towards you. So you know in that snapshot how fast every part's going. And then you can just continue to do that. But still, in just one snapshot is sufficient, because you know the speeds of everything moving. Does that make sense? So the velocities. Yep, good.
I'm going to put you on the spot. There's been some measurements of the cosmological constant over the last couple of years or so, and then there's been some disagreement. They're basically two end members, and the disagreement
tension.
is quite significant. And so what is your thought? Is there some new physics behind this, or is it some problem in their measurements, or is there something else?
So the disagreement isn't in the cosmological constant, but it's in the Hubble knot, so the Hubble flow, which we get out of those equations. And the disagreement is between very early universe and very late time universe. You get a different number. And so in the very early universe, it looks like it's going a lot slower than in the very later universe. And that could be observational effect, it could be mathematical effect, it could be a real thing that's happening in the actual universe. But the important thing is that the disagreement isn't insanely large. So up until a few years ago, it wasn't a consensus that there was a disagreement at all until these new observations have come up. But what is important to note is that the late time universe is what we do with supernova cosmology and baryonic oscillations and AGN reverberation mapping, which is a whole lot of words, but it basically means we're measuring how far things are away. But there could be some faults in our models. So the type 1a supernova I mentioned, they might not be perfect standard candles, and we could get biases from them. You may have heard of Adam Rees, who's a Nobel Prize winner. He standardizes his using Cepheid variables as well, so there could be error coming into that. That's where you get the 5 sigma tension. So there could be something interesting going on, or it could just be our observational effect of our universe.
Okay, how about, okay, one more after this. Yes.
There was some before you mentioned about the universe not going to rip us all apart and things like that. I understand that there's some thought that the expanding universe and the speeding up of the universe expansion is caused by dark energy. If that's the case, then is dark energy increasing? And if it is, will it get to a point where there's no atomic matter anywhere because everything's so far apart and pushed away? God knows where it goes to. But anyway, does that sort of fit in with your thoughts of the fact that we won't eventually get ripped apart? Like not only the galaxies, but also the solar systems and those within it?
That's a really good question, and it's a little bit tricky because although we're expanding and we're accelerating, the dark energy density per whatever unit volume you want to mention isn't changing. It's just becoming the dominant factor of that unit volume. So luckily, it's not something that is actually changing throughout the universe. It's, like I said, if you were to pick apart space and time, it's this rule that is built into space-time itself. And so now we're in a universe that's accelerating. The amount of dark energy per meter squared or cubed hasn't changed, but it's pressure, so it's always pushing outwards. And if I were to go back to the early universe and put a lot of matter in there, then it wouldn't have that much effect. It's trying to press, but there's too much matter, it can't press it apart. But now if I am to start stretching the universe just very slowly across billions of years, and matter is falling out of that meter cubed, so now I've got less matter density, the dark energy can start to win and it can start to push apart. And so dark energy isn't increasing, its effects are increasing on our volume, on our energy densities. And so we're probably not going to get ripped apart, because if you do the equations, it takes an incredibly long time, because at the moment it only happens on very large cosmological scales, like very, very, very large cosmological scales, on superclusters and groups, not on me and you. I'm not going to fly backwards all of a sudden. And for something like that to happen, it would take, an insane amount of time that actually, before that even happens, all of the stars in our universe are going to run out of energy. All of the black holes are going to evaporate. There's not going to be much left there anyway, which is also a sad ending to the universe. But, yeah.
Thank you. Just as we wonder what the beginning is, but also wonder what the end might be, if there is an end. Thank you.
You're welcome.
Thank you.
So the big rip, as I understood it, was more of a pull away, where matter and energy just couldn't interact because the universe was expanding faster than light speed.
So that's also another theory of the end of the universe, is if the matter can exist long enough for that to happen, then the fundamental forces, so we've got 4 different forces, gravitational, weak, strong, and electromagnetic, then they can no longer interact with each other. But probably not going to happen, thankfully. But that's another ending of the universe. You're absolutely correct. So there's all sorts of ways that the universe could end, and it depends what gets there first. So do we run out of matter? Do we have too much dark energy? Or do we decouple our fundamental forces again?
All right, I think we have the last question here. Did you stop? Yep, okay, good.
You mentioned that the WIMP seems to be the candidate for what dark matter is, but are there any other candidates or any other ideas of what dark matter might be?
Absolutely. So the WIMP model is the favoured model at the moment for reasons that sort of hark back to the dark matter, the annihilation, so the particle production in the early universe. So from cosmology, we know the fraction of dark matter that needs to exist to recreate the universe that we look at and see today. And so there's a certain point that we call WIMP freeze out. And so that means that the energy of the universe has cooled to a point where it can no longer create particles of a certain energy. So particles are still popping in and out of existence, but the universe no longer is hot enough to create particles at certain energies. And that puts a limit on the masses that the dark matter particles can actually be. And so the WIMP model actually fits really well with the mass that we expect. So it's about 1 to 100 gigaelectron volts per c squared in particle physics units, which is 100 times the mass of a proton. But there are a myriad of other theories that people have come up with. So there are things like sterile neutrinos, which are sort of baryonic, but they're incredibly, incredibly small, and they have very, very weak interactions. So they're electrically stable, but they also have the ability to recreate the gravitational effects that we see dark matter have on our universe. There was a theory called machos, so massive compact halo objects. That was essentially ruled out by the Macho project, so they went searching for these things called gravitational lenses, which is where the gravity of an object actually morphs the images from a background object. So when photons come from a really distant galaxy and they pass through something that has a lot of gravity, then it actually affects the image that you then observe with your eyes. And so they were searching for these gravitational lenses and they didn't find any that fit with the theory. So they sort of ruled out brown dwarfs and these range of things. There are some people that believe primordial black holes are an option. So tiny, tiny black holes about the size of a marble that could be flying through you all right now. And, you know, black holes seem big and scary, and we know that you can get pulled over an event horizon into a black hole and stretched out into spaghetti, and that all sounds very terrifying, but primordial black holes are so small that they wouldn't do any of that to you. So that's another particle physics candidate. But the WIMP one is the most compelling at the moment, so that's what I'm focusing on for my research, and that's sort of the one I know the most about.
Oh, great. So any other questions that people have, you can come down and feel free to talk to both Grace and Sarah. Let's give them a hand again for great talk.